Good morning. Today we will discuss the operations performed on different variables, signals and system. Operations performed on different variables. So first we will discuss the amplitude scaling. So suppose the x of t is the continuous time signal, then the signal y of t is the output signal, and therefore the resulting by the amplitude scaling, if the x of t is the continuous time signal, the output y of t resulting from an amplitude scaling applied to the x of t is, we can write like this: y of t is equal to c into x of t, where this c is thus called the scaling factor. This c is called the scaling factor. So this is equation number 1. So the value of y of t here is obtained by multiplying the input signal by the scalar c for each instant of time. Therefore, the physical example of amplitude scaling is the electronic amplifier. This is the electronic amplifier. So resistors also perform the amplitude scaling. If suppose the resistor is there and the resistors also perform the amplitude scaling when x of t is current, x of t is current, and y of t is the output voltage. Suppose here it is a resistor. Okay, so x of t is the current. When x of t is the current, this R into I of t into V of t. So this is resistance is also called as the scaling factor. So when this scaling factor is the resistor and y of t is the output voltage and x of t is the current. So in a similar manner, for discrete time signal, we can write for discrete time signal, we can write y of n is equal to c of x of n. So this is for the discrete time signal. So this is the operation amplitude scaling. So the second operation will call the addition operation. Addition operation. So let's suppose there are the two signals, x1 of t and x2 of t. So this is a pair of the continuous time signal. This is the pair of continuous time signals. Then the signal here y of t can be obtained by the addition of x1 of t and x2 of t. So there the output signal y of t can be obtained by the addition of x1 of t plus x2 of t. Okay, so The physical example of a device that adds the odd that's that add the pair of the continuous signals is the audio mixer. The audio mixer will give you the output by the addition of the incoming signals, whether it may be the 2, 3 like that. So this is called as the audio mixer, which will use the operation addition over the given function. So next of uh, this we can also write for the continuous discrete time signal. For discrete time signal, we can write here y of n is equal to x1 of n plus x2 of n. So this is for the discrete time signal. Next operation we will consider the multiplication. So operation this operation again let us consider the pair of the continuous time signal, that is x1 of t and x2 of t. This is a pair of the continuous time signal. Then the signal y of t can be obtained by the multiplication of these two signals, x1 of t and x2 of t. And for each prescribed time t, the value of y of t is given by the products of the corresponding values of x1 of t and x2 of t. So the example for this is the AM radio signal. AM is this is the amplitude modulation. So the AM radio signal is the example of the multiplication, that is by taking the product of the corresponding signals, in which this x1 of t is the x1 of t is the an audio signal plus the d plus a DC component, and this x of t is the sinusoidal signal called the carrier uh, carrier wave. We can also call it as a carrier wave. So in this way, the output signal for the amplitude radio signal consists of x1 of t and x2 of t. The x1 of t is the audio signal plus the DC component, and the x2 of t is the sinusoidal signal, which is called as the carrier wave. So for the discrete time signal, the multiplication operator can be written for discrete time signal y of n is equal to x1 of n and x2 of n. The next operation is the differentiation. differentiation. So let's again x of t is a continuous time signal. Then the derivative of x of t with respect to the time we can write here with respect to time, that is x of t, which is equal to the output signal. So in this way we have to differentiate the given continuous signals. Here the example of this differentiation signal is nothing but the your inductor. An inductor, so inductor performs differentiation. Inductor performs let us consider this is the inductor, suppose, and here the voltage we have applied here. The current flowing from this is I of t. This is the inductor L, and therefore the voltage across this inductor can be written as VL is equal to L into d dt of I of t. So this is the example of differentiation. Next is the integrator, or we can say it is a integration. So again, let x of t is a continuous time signal. And suppose for this is a capacitor, we have applied here again voltage V of t. The current is flowing through this. Now we have to write the output of this. So output of this is nothing but by the integration of this signal from minus infinity to the given time t, then x of tau into d tau. So this tau is the integration variable here. And for example, the capacitor perform the example of integration is here the capacitor. The performs capacitor performs integration. Suppose let the current flowing through the capacitor is I of t, and we have to find voltage across this capacitor, that is V of t. So the output is here V of t, and therefore it is 1 over C, the integration over minus infinity to t. This is I of tau into d tau. So this capacitor perform the integration function. Next is the operation performed on the this we have considered the operation which is performed on the operation performed on not these different variables. Um, this is the operation performed on dependent variable. The operation performed on dependent variable. Now we'll discuss the operation performed on independent variable. Operations performed on the independent variable. So first is the time scaling. The operation performed on the independent variable is the time scaling. So let us again consider the x of t is a continuous time signal, and therefore the signal y of t is the output signal, is obtained by scaling the independent variable time t. So here t is the independent variable. So y of t is obtained by scaling the independent variable time t by the factor a. Therefore x of a of t. So this is a is a scaling factor. And this t is the independent variable, and therefore here if a is greater than 1, if a is greater than 1, then this y of t signal is a compressed version of x of t. If a is greater than 1 here, then y of t is a compressed version of x of t. If suppose here a is less than 1 but greater than 0, then signal y of t is an expanded version of x of t. So these two operations, that is a compressed version as well as the expanded version, will discuss now. But in discrete time case, we can write y of n is equal to x of t. So here this is the time scaling for the discrete time signal, where this k is greater than 0 here. So this is a 1, this is 1, and this is suppose the input x of t. If your signal is like this, then the compressed version of this signal is that a should be greater than 1. So here y of t should be greater than 1. Therefore, it is a 2t. So if it is 2t, then what will be your compress version? Now, if you put here your time is 1, and now if you put here the scaling factor 2, then your signal will be like this now. So this is a half, this is minus half. So this is the compressed version of the continuous time signal x of t. This is the compressed here x of t is compressed by a factor of 2, where this x of t is compressed by the factor of 2. Now we have to expand the output. If we are to expand the output, your value of a should be less than 1. It should be less than 1. So we'll consider, we'll take here it is a half, suppose. Okay. If it is a half, suppose, then how your output signal will become now? This is y of t, this is 0. So here if you so this is minus 2 and this is plus 2. So this is called as the compress, sorry, this is a expanded, previous was the compress. So this is version of x of t expanded by a factor 2. This is expanded by the factor 2. So this is a time scaling factor. Now let us consider one example. Suppose the example is given is, suppose this is a x of n, this is 1, at 0 is 1, at 1 it is half, at 2 it is again 1, at 3 it is half, at 4 it is again 1, like this. Similarly, same case on the negative side, this is minus 1, minus 2, minus 3, minus 4. So We'll consider the effect of scaling on the discrete time signal. Now this is x of n. Now we have to find y of n, and now here we will multiply the n by 2. We'll multiply the n by 2. So now when you multiply this input by 2, so this 2 into 0, so it is a x of 0. So x of 0 is 1. So this is a 0 value. So x of 0 is 1. Now suppose 1 at 1 it is half value. If you put here half, it will be again x of 1. So if you put here half, so it will be 1. So x of 1, here it is a half value. Therefore it will become at 1 is equal to 1, because we have put here y of 1 is equal to x of 2 into half. Okay. So at x of 1, the value of it is half. This is x of, it is a 1 magnitude. So it is a 1. So for 1 it is a 1. Now consider the 2. At the 2, what is the value of n? X of n is 1. So this is a x of 2. For x of 2, it is value is 1. Now for x of 3, if you put n is equal to 3 here, what is the value of x of n at 3? It is half. So it is again 1. So this is again like this. So for 4, it is also like this. Similarly, case for the -1, -2, -3. So this is the reflection of the input signal by the scaling circuit. Thank you very much.